So by this point, we've introduced lines, the overarching principles of mark making, and the all-important ghosting method. And you've gone through the assigned homework exercises for the line section as well. So let's take a look at what we've learned and apply it to something new, ellipses. All the shapes you see on this page are ellipses. Some of you may think, oh, I know those are ovals. But the argument that I want to make today is that they are all, in fact, circles. A circle is a shape where any point along its perimeter is the same distance from its center as any other. It's going to be the same height as its width, so any rectangle we draw enclosing it on all sides would itself be a square. Pretty obviously, most of the shapes on this page don't fit that criteria. But what if we took a circle in 3D space, like this disk, instead of the 2D space of this page? Unlike the drawings on the page, it can be moved around in all 3 dimensions of space, and it can even be rotated on all 3 axes. Everything we learn in this course is about taking things that exist in 3 dimensions and learning how to draw them on a flat surface, such that they still look to the viewer as though they're 3D. In order to do this, we have to learn what happens on the 2-dimensional page when a 3D form is moved around and turned about. What we see here is a circle, but if we focus on what we would actually draw to represent this circle from observation as it's rotated in space, you'll notice that it actually gets squeezed in one dimension and takes on an elliptical shape as it's rotated. An ellipse is just a circular shape that has been squeezed down by anything from nothing, so a circle itself is still an ellipse, to being squeezed down into a straight line. We call the width of an ellipse its degree. If you're familiar with geometry, we use degrees to express rotation. And this is no different, because the width of an ellipse changes based on its rotation relative to the viewer. An ellipse with a degree of 0 is just a line, because we're viewing the circle from the side. An ellipse with a degree of 90 has rotated a full 90 degrees to face us head-on. Note that as the disk is moved around in space without rotating it, the degree of the ellipse gets wider, allowing us to see more of its face, because the angle in question is the one between the viewer's angle of sight and the orientation of the circle in space. As the circle moves around in the world, this angle changes, even if the circle itself is not rotated. So you can see here that when you're looking down the edge of this circle, there's nothing to be seen on either side of it, but as you move it to the side, you can start to see a little bit of its face, so that degree of the ellipse is actually getting wider. This is important to consider because if we were to depict a tube running straight across our field of view, we wouldn't be drawing the ellipses with all the same degree. That degree would change as we sample different cross-sections along the length of the form. So as you can see here, in this incorrect example, you've got the same degree on every ellipse that we look at along the length of this cylinder, and they're all the same, and that's incorrect. Instead, they would open up as they get further to either side of the viewer, because the actual angle between the viewer is opening up between the viewer and the circle itself. The last thing I want to introduce you to is a piece of the anatomy of an ellipse. It's called the minor axis. The minor axis is the line that cuts across the ellipse's narrowest point. So if we were to look at the different spans across which you could measure this ellipse, if we were still to pass through the center, then the narrowest point would be maybe about here. My pen is dying on me. So the minor axis is the line that cuts across that narrowest point, cutting it into 2 equal symmetrical halves. So the idea is that if I were to take this and fold it over, it would line up perfectly and you just end up with this. Ellipses also have a major axis that runs across the widest point, but ironically, it's the minor axis which is the most useful to us. Just as an ellipse represents a circle in 3D space, the minor axis also bears an important relationship to something in 3 dimensions. If I were to take a toothpick and pass it through the center of my disk, you'll find that the toothpick is sitting about perpendicularly to the face of the disk itself. In physics, this is called a normal vector, but for those of you unfamiliar with that term, you can just think of it as the line in 3D space that is pointing straight out from the circle's surface, not slanting one way or another. The minor axis of our two-dimensional ellipse that we drew on our flat page represents the normal vector in 3D space, just as the 2D ellipse represents the 3D circle. So if I were to put down another ellipse, that was poorly done. If you were to picture this ellipse as being in 3D space, being an actual circle, then this line here would be the one coming off its surface, just as this toothpick does. This may seem kind of arbitrary right now, but it's actually extremely useful, because it allows us to align our ellipses relative to something that exists in the 3D world. If we know what direction the normal vector should be pointing, then we can draw it on the page and use it as the actual minor axis of our ellipse. So for example, if I draw that line first, then I can draw an ellipse that tries to align to this line. With a minor axis on the page, it is just a matter of drawing the ellipse so that it is cut into 2 equal symmetrical halves down its narrowest dimension by this line. And that's precisely what I did with the cylinder. You can see that I've got this straight line going straight down the middle. I've aligned all of these ellipses to it so that I can know that they're all going to be parallel to one another in the world. Because if you were to have a cylinder, I have another poorly cut out disc. If you've got a cylinder, which is basically just 2 circles connected by a tube, you want to make sure those circles are parallel to one another and not, awkwardly angled, because then they'd look skewed. So you want to make sure that they are parallel. It's like this toothpick in the minor axis forms the actual spine of the cylinder. And if the form as a whole rotates with that minor axis and that normal vector, then both ellipses will turn accordingly. Now, I fully expect that what I just explained is going to cause more than a few headaches, because this is the first point in the course where you're breaking down the barrier between 2-dimensional space and 3-dimensional space. I don't expect you to understand this immediately, but by laying down the theory behind these concepts, we're starting to plant seeds in your brain. The next step, once you've read through the written content for this section, is to water those seeds by working through the assigned homework exercises. Speaking of which, when you do those exercises and draw your own ellipses, there's 2 things I want you to remember to do. The first is to simply draw your ellipses from your shoulder. You can't see my whole shoulder right now, but I've got a whole video about it, how you can use your whole arm to draw, but I want you to make sure that you're not drawing them from your wrist, because these ellipses require the kind of smooth, fluid, even shapes that we can get from using our whole arm, not the kind of stiff precision that we can get from using our wrist. So if you were to draw it using your wrist, you'd have a very limited range of motion, and your ellipse will probably come out pretty uneven. If you draw it with your shoulder, you can draw bigger ellipses, smaller ellipses, it doesn't matter. It will come out more smoothly. Even the small ones can be drawn from your shoulder. The other point is that I want you to use the ghosting method for these ellipses, and frankly, for every mark where you're better off using your whole arm, use the ghosting method too. It'll help you to get into the habit of thinking before you draw and weighing how each and every mark contributes to a given drawing, so you don't have to put marks down wastefully. Of course, it'll also help you increase your overall control while allowing you to execute your marks confidently. To that point, remember that executing your marks confidently doesn't mean as fast as you can. It just means that you're drawing with the sense that you're always pushing yourself forward, not hesitating or trying to steer things with your eyes. As you can see here, I'm applying the ghosting method, but my execution isn't going nearly as fast as I could go. I'm just keeping an even pace. I'm always moving forwards. And there you go. It's still pretty smooth. It gets a tiny bit hesitant, so you will have to weigh, am I slowing down so much that I can't be confident at this pace? You will have points where you will inevitably start to wobble, and so as soon as you catch that, speed up a little bit more, but keep focusing on the fact that it's not just about speed, it's about being confident. So I can ostensibly draw a line that just continually moves forwards without very much wobbling, even though it's at a slow pace. Of course, had I sped that up a little bit, because that was a little below my threshold, it would have been smoother. So that about wraps it up for ellipses. Again, make sure that you read through the text as well. It goes over the same concepts I've explained here, but going through them in different forms and formats will help you wrap your head around them more easily. And of course, going back over videos, going back over the notes and whatever, even if you've watched and read them already, is always a good thing. It will help keep the information fresh in your mind, especially as you go through these exercises, which may take several days, depending on how much time you have anyway.